In this example, we're going to use our multiplication properties of polynomial to simplify these identities. So here we have this binomial times this binomial. So if we use our distributive property, this becomes cotan squared x minus cotan x cosecant x plus cotan x cosecant x minus cosecant squared x. These two terms here will cancel since they're identical but opposite signs. So we're left with cotan squared x minus cosecant squared x. We know another of our Pythagorean identity is that cotan squared x plus 1 is equal to cosecant squared x. So we can replace all of this. So we have cotan squared x minus 1 plus cotan squared x. Using our distributive property again, we have cotan squared x minus 1 minus cotan squared x. And these two will cancel, so our final answer would be equal to -1. Here we're simplifying the sum of two trigonometric expressions by using our fundamental identities and once again some of our algebraic skills. Since we're adding two unlike fractions, we need to have the same denominator. So to find our LCD, we can multiply this denominator by this. So our LCD will be tan times 1 plus secant x. So to make the denominator the same, we can multiply this one by secant x plus 1 or 1 plus secant x, and this is 1 plus secant x. If we simplify this or use our distributive property, this becomes 1 plus 2 secant x plus secant squared x. And this is all over tan x times secant x plus 1. On this side, we can multiply by tan x. Multiply both the top and the bottom by tan x. So this side becomes tan squared x over tan x times 1 plus secant x. Now since both our denominators are the same, we can add the numerators and keep our denominator. So this becomes tan squared x plus 1 plus 2 secant x plus secant squared x all over tan x secant x plus 1. We know tan squared x plus 1 is one of our Pythagorean identities, and which is equal to secant squared x. So all this will become secant squared x. So secant squared x plus secant squared x will give us 2 secant squared x plus we have 2 secant x all over tan x times secant x plus 1. Now on the top we can see that we have a GCF of 2 secant x. Pull this over here. So this becomes, if we factor out our GCF, we have 2 secant x times secant x plus 1 all over tan x times secant x plus 1. From this we can see that this will cancel with this, leaving us with secant x over tan x. We know secant x is 1 over cosine of x, and we know tan x is sine over cosine of x. So the cosines cancel, so this becomes 2 over sine x. We know the reciprocal of sine is cosecant, so all of this simplifies to give us 2 cosecant x. Here we're using trigonometric substitution to simplify an algebraic expression. Our algebraic expression, given its just radical, we're finding the square root of 16 minus x squared, and we're told to use x is equal to 4 sine theta. Now if x is equal to 4 sine theta, we can substitute for x. So this becomes the square root of 16 minus 4 sine theta when we replace x. This is being squared. So if we remove our parentheses and square everything inside, we get 16 minus 16 sine squared theta. Here we can see that we have a GCF of 16. So if we factor out 16, we're left with 1 minus sine squared theta. We know from our Pythagorean identities that 1 minus sine squared theta is the same thing as cosine squared theta. So this becomes the square root of 16 cosine squared theta. The square root of 16 is 4, and the square root of cosine squared theta is just cosine theta. So our final answer is 4 cosine theta. In this example, we're gonna use trigonometric substitution to simplify an algebraic expression, and also to find sine theta and cosine theta in this equation. Here, our equation is negative 5 square root of 3 is equal to the square root of 100 minus x squared. We're told that x is equal to 10 cosine theta. Now, similar to our previous problem, we're going to replace x with 10 cosine theta, and then we're going to square it since it's x squared. So this will give us the square root of 100. When we square this, this becomes minus 100 cosine squared x. We factor out 100, this becomes the square root of 100 times 1 minus cosine squared theta. And we know from our Pythagorean identities that 1 minus cosine squared theta is the same thing as sine squared theta. So this becomes the square root of 100 times sine squared theta. From this, we have the square root of that is 10 sine theta. So we know that negative 5 square root of 3 is equal to 10 sine squared theta. Divided by 10, we get sine theta is equal to negative square root of 3 over 2. So here is our required sine theta. So we're actually find sine theta, which is negative square root of 3 over 2. Now we're also trying to find cosine theta. And we're told that our angles are from negative pi over 2 to pi over 2. So this is in our first and fourth quadrant. So here we go from pi over 2 to negative pi over 2. Go back to our unit circle. This is equal to 5 pi over 3. Our sine of negative 3 over 2 is equal to 5 pi over 3. So here we have our sine, which is negative square root of 3 over 2. For 5 pi over 3, we know the corresponding cosine value for that is 1/2. So the cosine of 5 pi over 3 is 1/2. So the cosine of theta would be 1/2. Since theta is equal to 5 pi over 3.